Hello everyone, Mr. Fig back again. I wanted to do some demonstrations of refractions. We've gone through the presentation, there's been a lot of diagrams, but it's always nice when we can see physics in action. So what I have here is a piece of paper with a circular protractor printed on it. Basically just a reference of 360 degrees around. And I have my laser ray box again, which should create a light source that is bright enough to appear on camera. And we can see that the laser beam gets sent straight out across this reference paper. Now, the first thing I want to do is just place a piece of glass on the paper, and I'm going to place the glass so that the light strikes it head on. And you can see here that there is no bending the light, so the light comes straight in the glass and exits the other side. So you might be asking yourself, well, did Mr. Fig lie about refraction? And I didn't. That's because right now our angle of incidence is 0. So the normal line is this perpendicular line from where the light is striking the edge of the glass. So right now I have no angle of incidence, so I have no angle of refraction. But things will be different if I rotate the laser beam and I'm going to strike the light at the same point. So again, here is my normal line, and this black line here, that represents my normal. The light strikes the surface of the glass, and you can clearly see inside the glass the direction of the light ray is bending. Now, so that's refraction in action. But you can also see coming out the other side that the light ray bends again. In fact, if I use a ruler to line up on the original laser beam, a little tricky to do as I'm filming, but you see that inside the glass I have bent away from the ruler and towards the normal line. Here would be the normal line in the glass. That black line you can also see through the paper. So the crisscross is this this line right here is our normal line. So here was the incident direction of my ray, and I bent inwards towards the normal line. But I can do the same process on the other side. And here is the original light in the glass, and when it goes into the air, it's bending away from the direction that was traveling. There's no normal sign. I could draw a normal over here, but you get the idea. So it's actually very hard to, just using a square piece of glass to measure these angles of incidence and refraction, because the light bends in the air again. It's also why I don't see the change of color, the change of wavelength that we've been discussing, because I'm out here in the air. I'm not inside the glass. So the wavelength inside the glass is changing. It's not this red. But it's just when that light escapes the glass back into the air, it goes back to the original wavelength, and so I just see the original red light because I'm not actually inside the glass. But I can use geometry to make it a little bit easier to measure the angles here. I'm going to replace the rectangular piece of glass with a half circle. Now, notice something interesting happens. The light doesn't bend coming out the half circle any longer. Now, the reason why is because, again, as we talked about spherical mirrors, I'm making sure that this light beam is striking exactly the center of the half circle, which means the ray is passing through what would be a diameter of the circle, which means the light ray is hitting the sides of the circle perpendicularly along a normal line. So it has no angle of incidence striking from glass to air, and it goes straight through. Now, if you take a look at this, I have an angle here. Oh, that won't work. Let's see. If I measure this angle here, I'm going from 180 to 220. So that's 10, 20, 30. This is 40 degrees. And that would be my theta incidence. On the opposite side of the refraction, here I have 10, 20, oh, it looks about 28 degrees. So theta r equals 28 degrees. Oh, sorry, that's a mess because I shifted my laser. Sorry, that would be more like, so 10, 20, 30, 40, 10, 20. Sorry, that's closer to 25 degrees. Here we go. So I have an angle of incidence. I have an angle of refraction. I can actually solve for this, the index of refraction of this glass. Let me just do it on another post-it. So my incident material is air. So I have n air sine of 40 degrees equals n glass sine of 25 degrees. That means that the index of refraction of the glass is going to be n air sine 40 divided by sine 25. But n air is just 1. So the index of refraction of this glass is the sine of 40 divided by the sine of 25. So I calculated this earlier, but let me just double check my numbers. And I get that the index of refraction of this glass is 1.52, which is what we expected. So here I'm seeing refraction in action. Now, the interesting thing is, normally I could not stick my light source inside the glass, so it would be hard for me to normally have the incident material be the glass. But this particular shaped glass allows me to do it. So I'm going to try to keep my angle 40 degrees and striking the center of the circle again. But now what I'm going to do is I'm going to flip the glass around. Now, some interesting things are going on. Let me straighten this out. There we go. Okay. Alright, so here you'll notice that the light isn't bending going into the glass because, again, I'm making sure that it hits the center. So this is on a normal line as far as this curved side of the glass is going on. So my angle of incidence here is still 40 degrees, but now my incident material is the glass. Beyond the flat side, the refractive material is the air. Now notice what's going on with the light ray now. You can clearly see that I'm bending. Here is my normal would be measured from this point. This is my boundary between glass and air. And you can see that I am clearly at a larger angle on the air side. The light ray has bent away from the normal line. In fact, it's at 10, 20, 30, 40, 50, 60, looks like 70 degrees. And I could actually calculate the index of refraction with these angles as well, going from glass sine 40 equal to air sine 70. I should get a number close to what I got before, at least to 2 sig figs with this setup, because the laser beam spreads out a little bit, so it's hard to get it down to the tenth of an angle, tenth of a degree. So there you go. There's refraction in play. Now you can already see the beginnings of a reflection occurring from the surface as well. And we said that it's not just refraction. Reflection occurs as well, but most of the light's being refracted. But if you recall, we talked about also a critical angle. Now, if I use 1.52 for glass, I can calculate the critical angle going from glass into air. So I would have n glass sine, oops, let me get that lower so you can see. N glass sine of the critical angle equals n air sine of 90. But the air is 1. So basically, sine of the critical angle is equal to 1 over n of glass. Or the critical angle will be equal to sine inverse 1 divided by 1.52. Well, I can do that on my calculator. So I have 1 divided by 1.52. Oh, am I in? Hang on, I'm in radian mode for some reason. There we go. I get that the critical angle here is about 41 degrees. Well, putting back my experiment back together so we can see what we're doing. I'm at 40, which is very close to 41 degrees. But watch what happens if I go just a little bit further away. Now, I'm basically, you can see, about 42 degrees. So I've only gone 1 degree beyond the critical angle. And now look, there is no light coming through the other side any longer. It is all being reflected. That is, and that you can see inside the glass, it's the same angle. So what we're looking at here is an example of total internal reflection. Once I got beyond that 41 degrees, the light no longer refracts into the air. It just totally internally reflects. Now, I can also see that if I, that explains what I'll see if I use this triangular piece of glass. Notice no light's coming through this side of the glass. Again, this is a 45-45-90 triangle. So here the light goes straight into the flat side, so no angle of incidence. That means that my angle here is at 45 degrees, which is larger than that 41 degrees. And so I have no refraction, I have total internal reflection. In fact, I can undergo total internal reflection multiple times inside the glass. And you'll see that the light comes in, totally internally reflects once, totally internally reflects again, and then comes out when it comes straight out the other side that it came in, and I'm basically making the light make a U-turn. A similar effect happens inside of a glass fiber. In fact, I should have a glass fiber, so hang on one moment. Now, I'm holding in my hands a piece of glass fiber. Now, this is much thicker than what's used for internet or communications. It's probably about the same thickness of now it's probably even thicker than what they would use on medical use. So, probably, possibly used to connect stereo equipment in the house, because sometimes you have optical hookups. But I'll hold it under the main camera, and you can see it's a very thin fiber. It's black because it's coated in plastic to protect the fiber. You probably can't see much coming through the end of the fiber there because there's only so much resolution in the camera. But what I'm going to do is I'm going to hold this under the camera and I'm going to tie it in a knot. So you see I've knotted it up. I'll knot it up again. So this fiber is tangled up. Now I have here a green laser pen. So I'm just trying to find the other end of my fiber. So hang on. Alright. And I can shine the laser onto the paper and you see it's very bright. Probably a little bit brighter for what the camera is registering right now. But what I'm going to do is shine it into one end of the cable and you'll see it come out the other. And there it is. So turn off the laser. No light comes through. Turn on the laser. And you see the light coming through the tip of the fiber optic cable. And there you go. Fiber optics in action from total internal reflection. All right, good luck with everything, and I'll see you next week when we start talking about lenses.